All right, welcome everybody. Thank you very much for being here, both people in person and online. So it is a great pleasure, it is a privilege to have Dr. Linda McIver with us this morning from the Australian Data Science Education Institute. Linda is a pioneer in the teaching of authentic data science and computational science education. She's the founder of the Australian Data Science Education Institute. She founded it in 2018. She's the author of Raising Heretics, Teaching Kids to Change the World. She has appeared on a Q&A. She regularly delivers engaging professional development for primary, secondary, and tertiary educators across all disciplines. Linda is a passionate educator, researcher, and advocate for STEM, equity, and inclusion. She's got a PhD in computer science education, and she has extensive teaching experience. Linda's mission is to ensure that all Australian students have the opportunity to learn STEM and data science in the context of real projects that empower them to solve problems and make a positive difference to the world. So I know Linda primarily through her amazing podcast called Make Me Data Literate, which is an absolute fantastic podcast, and as a weekly or a regular cheerleading, like yes, as recently as last week, her interview with Michael Broad was just a fantastic, roaring agreement episode, and I recommend everybody checks it out. So it's a great pleasure to have her here today. She's going to talk about teaching data science. Thank you very much, Linda. Please take it away.
Thanks for the introduction, Lewis. That was lovely. I want to start by telling you a couple of stories that kind of illustrate the big goal here. This is a graph of my average daily step count per month, which was, I am glued to my phone. So the step count on my phone, we know the step counts are wildly accurate, but they're at least, I think, reasonably consistently inaccurate. So the trend was something useful to have. And I developed a really nasty hip problem. In my head, it all stemmed from when I tore my plantar fascia in the US in 2018, November 2018. And I was like, that's when it started, that's when it all started to go wrong. But this graph starts in 2016. And you can see that, it's very up and down, as these things tend to be. It's real data, it's messy. But the downward trend started in 2016. It was not my plantar fascia that kind of messed things up. It was already an ongoing process. And this is part of how I figured out that I had a congenital hip problem, same problem that my daughter had that was diagnosed when she was 16. They don't do the surgery that they do on 16-year-olds on people who are well over 40. So last year I had a double hip replacement and I can now walk. It's miraculous. But when my hip surgeon saw that, he was like, oh, that's amazing. I take grafts to my doctors. I would like to build a world where everybody takes grafts to their doctors, but apparently it's a little weird at the moment. But he was excited about it. He was like, that is classic. That's exactly the pattern that you see with this kind of hip problem, which is that you get ups and downs, but the overall trend is down. And it was pretty badly down by the end. When COVID hit the news and we started having attempts to communicate the severity of it and trying to understand why, this is actually a terrible screenshot because there's no labels, but cut me some slack. The numbers down the left are simply from the first case in Victoria. The numbers in the middle are the daily case numbers, and the numbers on the right are the cumulative case numbers. And, we had all these people going, well, one case, it's not so bad. 5 cases, it's not so bad. 11 cases, 26 cases. Like, why are we terrified of these numbers? They're not scary numbers. And they're not scary numbers if you don't understand exponential growth. right? But as soon as you understand exponential growth and you look at where the graph is going to go if this continues, you start to freak out, right? So we really, in some sense, needed people to freak out a little more than they did. And, we needed people to take it seriously. Why is it that exponential growth, which is a pretty simple concept and which is actually taught in schools, was something that nobody understood? I started making little videos and people were like, oh, I get it now. I'm like, that's great, but what are we doing wrong that you didn't get it before? Sorry, I should have given you a horror warning before that. Some years ago, I think it was 2016, I had a sleep study. And this is how they truss you up. They put, I think I had 16 different electrodes connected to me on my hands and on my feet and on my face and around my chest. They truss you up like that, and then they say, now sleep normally, which wasn't really a thing, but they gave me a report afterwards, and I had this wrangle with the specialist because I wanted the data. And he was like, you won't be able to use the data. And I'm like, try me. Anyway, I did get the data in the end, but they gave me a report afterwards, which basically used 3, maybe 4 of these electrodes, of the data coming from these electrodes. 16 electrodes I had, and they basically threw most of the data away and said, you have mild sleep apnea, you have a little bit of restless leg syndrome, and otherwise, we don't really know. And I'm like, you had 16 electrodes. Why was I trussed up like a chicken if you weren't going to use this data? And so I thought, well, this is clinical practice. If I get back to the researchers, they'll be doing more, right? They'll be really making the most of these 16 electrodes. And so I found myself some sleep researchers, and I went, no, we pretty much throw it away. I was like, we had, expert researchers in sleep. This is state-of-the-art polysomnography, which is how they measure sleep. This is the best known way of measuring sleep, and they were throwing most of the data away. And I believe that this is because those scientists did not know enough about data to really make the best use of those 16 electrodes. They were like, they did the classic newbie mistake, which you see in surveys all the time. We're going to ask all the questions, we're going to collect all the things, and then we'll figure out what to do with it. And what you do with it mostly is throw a lot of it away. It's very disappointing. So you've had the intro for me. I can pretty much skip most of that. But I have to give you a small apology, which is I'm going to rely more on my notes than I usually would today. And that's because since May 2022, I've had long COVID, and it does terrible things to my memory. And it means that I often can't find the word that I'm looking for. I have aphasia, which is very frustrating. And a couple of weeks ago, I got COVID again. So I make no warrants for the effectiveness or efficiency of my cognition at the moment. So I'm going to have to rely on the notes. On the podcast that Lewis referred to, Make Me Data Literate, the last question I ask is always, what excites you about data? And I love it because people get really passionate, and we've talked a lot about problems and misuse of data and all the bad stuff, and then we get to what's the good stuff. And the overall message is it's the power. It's the power to understand things. It's the power to explore things and to find things out, and often to solve problems. And there is no reason that power can't be in everybody's hands. I'm not going to turn the whole world into data scientists, but to give them the understanding that data is powerful, to give them a reason to want to collect the data so that we're actually collecting data about, this disease that's out in the world and causing, we don't know what harm because we're not looking. We should be looking by default. We should be measuring, we should be collecting data, we should be trying to understand the world. One of my students recently said to me, she said, "You're the one who gave me the confidence to play with data like silly putty." And I want everybody to have the confidence to play with data like silly putty and to just try and figure stuff out and to challenge the default narrative when people say COVID is over, to go, I don't think it is. You know, to actually have that power to understand the world and to challenge the accepted narrative. So that if we had large sections of the population suffering from cognitive decline as a result of COVID, we would know because we're looking for it. It astounds me that we're not looking for it. So I started my career as a computer science education academic. I want everybody to learn to code. But actually the code, it turns out, isn't the important part. I started doing what I'm doing to get more kids engaged with code. I was teaching computer science at a nerd school, John Monash Science School in Melbourne, and the kids didn't want to do it because we had this subject that was toys. So I started doing data to give them a reason to learn, and I'll talk more about that in a bit. When I went through my undergraduate degree, we had about 25% women in the class. A recent Monash report shows that between 2016 and 2021, there were 21% women in the CS degree, and that's just the women who start the degree, not the ones who drop out. And often they drop out because they're sitting next to men in class who've been programming since they were in the womb. And it's very intimidating. One of the cool things about doing data science in the high school classroom is that it levels the playing field, because you may have the kids who've been programming since they were in the womb next to kids who've never seen it before. But when you start talking about data quality and about visualizations and about misleading graphs, they haven't done that before. No one's done that before. And so you've got a really level playing field, which is quite powerful. In 2018, I started ADSI, and in 2019, I started to realize that critical thinking was the big deal. That's why I called my book Raising Heretics, because we want people to challenge ideas and challenge them on the basis of evidence, not data. So basically in 2019, I was building up to this big idea that we wanted people to do their own research and be skeptical. And then 2020 happened. And that wasn't a good look anymore. But it's really important that we be skeptical on the basis of evidence and data. And that if I come to you and say, I don't believe that, you should be saying, why not? Show me your evidence. And I should have evidence to show. It's something everybody should be able to do, data scientists or not. So some people see the numbers in computer science, the gender breakdown, as evidence that women just aren't good at this stuff. They're not interested in this stuff. They're not choosing this stuff. And in fact, a chief scientist in recent years, who I won't name because it would humiliate him, said to me at Science Meets Parliament one year, he said, we shouldn't be teaching technology in schools because the kids who are interested in technology will find it, like my son did, and nobody else needs to know. And that's Owen's in the front row going, it's terrible that attitude is still out there. But the women that we're missing are just the low-hanging fruit of the observable problem. We are also not getting the kids who believe that the boys who think that tech isn't for them because they don't like living in a basement eating pizza and drinking Coke. They want to talk to people, so they think tech is not their thing. We're missing the people who just don't see themselves represented in the industry, but we're also missing the people who don't see it as relevant don't see it as meaningful, and haven't got the motivation to push through the pain that is wrangling tech. And it shouldn't be that much pain, but that's a different talk and probably a much longer one. So what we're dealing with in the tech industry is often code systems that are designed by people like Sheldon Cooper for people like Sheldon Cooper, and they're not representative of the community as a whole. It results in technology like period tracking apps that tell their users that their periods are invalid. True story. Results in the joke that everything is a moment away from stalkerware. Everything in tech, is one iteration from stalkerware, because they have this great idea. Wouldn't it be wonderful if people could see everyone who's nearby? You only have to have one woman in the room to have someone saying that that's a bad idea, but frequently there isn't one woman in the room. But we're also missing the non-binary folks who don't see tech as relevant to them. We're missing all of the boys who don't see themselves represented, and just we're missing the people who don't see a reason to learn this stuff and who don't think it's powerful. So the big thing about data is about the power that it gives you to understand things, to change things, and to evaluate things, which is really important. So the problem is not just with the industry, it's the way we teach tech, because we teach tech as a matter of toys. We think, we were having this conversation before at coffee, we think that STEM is a matter of robots, and frequently most schools will do a one-day pull-out program of robots and tech toys and drones and say, tick, we have done STEM. And that's not STEM, it's playing with toys. And there's a big chunk of your audience who don't think those toys are fun. So not only are we not doing STEM, we're pushing people away from what we're telling them is STEM, because the kid who gets the robot that didn't quite work, or the drone that had a missing connector, or that, so they just spend the whole time wrestling with it. It doesn't work, it's not fun. And they come out further convinced that tech is not something they're interested in, and STEM is not for them. When we were teaching that year 10 subject that was toys, we were teaching with Scratch-based interfaces. We were getting them to program robots to push each other out of circles, to draw pretty pictures in Scratch. The number one piece of feedback I got was, why are you making me do this? It's not relevant to me. I hate it. I'm not good at it. I can't do it. And then we shifted to data science. And it was a tiny unit, and it was broken as all get out. It was the first run unit. They're always broken. We didn't have enough teachers who were really qualified to teach it. It was problematic in many, many ways. Nonetheless, you can see the shift in relevance from doing the Scratch-based stuff, which was just playing with toys, to data science. I apologize for these graphs. I haven't got access to the original data anymore, so I just have the graphs. But there was just a flip in relevance. Suddenly kids were coming to me going, oh, this is so useful. And I used this in my science project, which was actually part of the point, because the graphs in their science projects used to make me cry. I used it in my science project. I used it in my maths exam the other day. And, oh, there was a graph on the news last night, and it was outrageous. There was no 0 on the scale, and it was so misleading. I'm like, yes. Just getting them to think like that and to recognize that this stuff is a tool that they can use is why I started ADSI. So I figured out that I had found a way to engage kids with STEM. I had found a way to get them interested in this technology. And so I quit, because I wanted to make that available to all students, not just the kids in my classes. So that is the origin of ADSI. And what we do is we create lesson plans, and we build projects, and we train teachers to do this stuff. And as I said, I'm a computer scientist. I want everyone to learn to code, but I don't actually do much teaching of code. Most of what we do is in spreadsheets. And in fact, with the 5-year-olds, we've got them stacking blocks, and that's their graphs. The technology doesn't matter. What matters is this thinking skills, the understanding that no data set is perfect. So what's wrong with my data? I'll come back to that idea more in a minute, but I want to tell you first about Tia. Tia was one of my students early on at John Monash, and she's one of the reasons that I do what I do, because she came to us. The John Monash is a senior secondary school, so it's only 10 to 12. And she came to us in year 10. Her only experience of tech had been classes in Photoshop, where they got given an image and a list of functions to perform on the image and an expected output. And obviously she was really enthralled with tech. She hated it, couldn't see the point. And then instead of forcing her through the toys path, I had persuaded my boss to let me carve out a little kind of option for advanced kids where they worked with scientists to do some real stuff with data. She was all over it. She just loved it. And then she started coming to me. She did my year 11 subject where she worked with real data again, and she worked with some neuroscience data. Actually, it was in MATLAB, and I don't know how many of you have tried to wrangle MATLAB data in Python, but it is no errand for the faint-hearted. But she managed that, having no coding experience before she arrived at John Monash. And she presented it to the researchers who were like, those visualizations that you've done, that's exactly the way we present this data. It was data about neurons firing, and it was really complicated and messy, and she'd done this visualization that was exactly what they needed. And it was a fabulous moment. And that was just a year 11 computer science subject. But she was doing real stuff and she could see the point. So suddenly, from believing that tech was awful, Tia went on to do a science degree, but she did a graduate diploma of IT beside it. She's now a full stack developer at Style Education. And she's incredibly talented. She's incredibly skilled, and she loves it. She didn't believe any of that before she'd had the chance to do some real stuff. Next, we have Chris. Chris was in my very first class of year 11s. He was already a very talented and skilled programmer. And my boss, the head of faculty, believed that he was a problem because there was no way I could teach him anything, obviously. So we would have to, while he was doing my year 11 subject, we'd have to give him something else to do. So my boss arranged for him to actually do some work for a company, and he would sit at the back of my classroom doing his work. But because I was doing interesting stuff, he got further and further drawn into what we were talking about. He wound up doing a computational science project with a researcher by the name of Dr. Michael Gantier, who was working on cancer research. He's a molecular biologist. He had enough computer science to know what he needed, but not enough to do it, and not enough time to do it. So Chris teamed up with a student by the name of Matt, and they produced this software that enabled Michael to do in 20 minutes what normally took him weeks to do in terms of finding sequences in a database and stuff. And he was still using that years later. And now the thing about this software is that Chris and Matt were so enthusiastic about it that they kept working on it. This was in the year 11 subject. They kept working on it in year 12. And they got into trouble for it because they were told by their teachers that they should be focusing on what really matters, which is the ATAR, not on cancer research. What message are we sending the kids? That it's more important to optimize your ATAR than to do cancer research? I could have long conversations about the validity of the ATAR. There's a whole chapter on it in my book, but it was just a terrible message. They did extraordinarily well in the year 12, but they also did this, continued on this project, and it was amazing. And as far as I know, Michael's still using that software. Now this is Austin. I have his permission to tell this story, and he knows exactly how I tell it, and he loves it. In year 10, he was my nemesis. We were doing the toy approach and he was bored out of his brain. And so he was causing trouble. He was disruptive. He was sullen. He didn't do a stitch of work all year. And my boss's response to that was, well, obviously he needs to redo the subject, which was not attractive to Austin and even less attractive to me. Eventually, we managed to get him through the subject and drag enough work out of him that he, ticked the pass column, and he went on to do year 11 and to choose my subject. I was like, no, please, not again. And no, it wasn't again, because the first thing I gave them to do was to write a chatbot in Python. He came back after the first lesson, having never programmed in Python before. He came back with some 1,000 lines of a near perfect English to Pig Latin translator. And I broke it on rhythm and on Qantas. Qantas is cheating, but he went back and he fixed it and he commented the code and he made it more modular. And from then on, he just flew. He collaborated with another couple of students on a program called Dolphinote, where we had a computational science project, which was collaborating with an organization who runs dolphin tours in Port Phillip Bay. And they had 8 years of data about the dolphins in Port Phillip Bay, and it was handwritten. And the project was we would digitize some of the handwritten notes and see what we could find in the data. And Austin was like, this dealing with handwritten data has knobs on it. So he and his project partners, Michael, I've gone blank. That's terrible. Michael and his friend, they wrote a system where they had a server-side system which would collect the data. They had an app which the Polpero crew would take on the boat and record the data in, and it would feed back to the server side. The server would print out the forms that they needed to send to the Department of the Environment, but also collect the data and put it into a usable form. They wrote the most professional problem specification that I've ever seen. So it wasn't just the code. Austin was determined to do this properly. Again, his other teachers complained to me because he wasn't doing a lot in his other subjects, but he was giving everything to this. And it was a remarkable piece of software. Now, the last story I want to tell about my students is the final year at JMSS. Like, it's great that the kids were engaged in their work and, we made some changes and isolated examples, etc. We did a project this year. I worked with 3 different scientists to come up with different projects that they could do. And I worked with Sonika Tiagi, who is a genetics, bioinformatics person. And she laid out this project for them. And it was working with genomic information. Again, it was quite tricky, and they wanted to use machine learning to try and figure it out. A couple of days later, I got approached by a student named Victor who wasn't doing my subject. And he came up to me, he started laying out his credentials in code and in biology. And I'm like, I taught you last year, you're great, I know, where are we going with this? And he begged me, he said, please, can I do your assignment? He wasn't doing the subject, but he wanted to do the assignment because it sounded so good, it sounded so meaningful. And again, they continued working on it the next year. They had a poster at Lawn Genome Conference, which is a significant conference in the field. When you're doing stuff that kids who are not doing the subject want to come and do, that you have something powerful there. Now let's talk for a minute about science education. When we teach science at the moment, we have a nasty tendency to teach it as a series of facts and known processes and experiments where we know the outcome. So we teach the kids that what is science is facts, knowing things. We know that that's not science. Science is finding things out. Science is challenging the things that we know. Science is actually pushing the boundaries of knowledge, but we don't teach it that way. We teach it as facts, which really bit us hard in COVID when science was changing its mind. You know, we would understand more about COVID, and so the recommendations would change, and the public at large were going, look, see, science doesn't work because you guys are changing your tune. You're like, no, that is science doing exactly what it's supposed to do. But it's not what we teach. We teach them they have to memorize things. We teach them they have to know which is meiosis and which is mitosis. And I have a degree in biology and I still can't remember. We teach them that when they do a prac, they get two, known reagents, they apply a known process, and they should get a known result. And in fact, I was talking to an anonymous person, my husband, recently about the idea, because it came up on the last episode of my podcast, that the idea that we kind of fudge things to get the result that we want, which happens too much in data science as well. And he said, oh, well, in pracs, we always used to know that if you fudge your data, you have to fudge it a little bit wrong so that it looks real and it looks believable. You don't fudge a perfect curve, you fudge one slightly off. And I just kind of stared at him. But he said, doesn't everybody do that? Like, isn't that people nodding in the room, right? That's the way we do education. What are we teaching the kids? We're teaching the kids the important thing is to get the right answer. The important thing is you know what you're going to get, fake it until you get it. That is not an education in science. It is an education in confirmation bias. So we have to teach it differently. We have to teach the exploration. We have to teach things where people don't know the answer they're going to get and where they have to figure out whether the answer that they have got is in any way valid and what's wrong with it. And if you're using real data sets, that's built in. Because if you're using a real data set, you can't eyeball it and figure out what the average is. You can't know what your analysis is going to produce. And you can't look it up in the back of the textbook and say, have I got the right answer? So you have to critically evaluate your own work. You have to be able to justify your work, and you have to say where it's wrong. And that is an incredibly important part, which I'll come back to in a minute. But this is another student story. I lied when I said I wasn't going to tell you any student stories. In the last year I was teaching, we did an experiment where we taught tech and science together. So everything at that school was pretty much team taught. So you had two teachers in a room anyway. So we decided, let's try teaching science and tech together so that we can really build the connections in. And so I was teaching with a physics teacher. And she was amazing, but physics is not my strong suit. So in fact, I hated it at school. It's my worst subject in year 12. And so when we were teaching physics, Catherine would take the lead and I would just roam around and see who needed help. And there was a group of girls in that class who believed very strongly that they could not do physics. But the way Catherine taught it was so clear, and you could see the relationship between distance and speed and acceleration. You could see it so clearly that suddenly, for the first time, I understood it. And so I said to these students, come hang out with me at lunchtime. I can help you. I can help you understand this. It'll be fine. And they were like, how many weeks are we talking? I was like, no, really, one lunchtime, we'll do it. This was all we did of physics that year. It was just kinematics. It was just these three graphs, these three equations, but they believed they couldn't do it. So we sat down one lunchtime and I took them through the distance thing, I took them through the speed thing, I took them through the acceleration thing, one at a time, broke it down to bits. They were like, okay, yep, we got that. That all makes sense. That's easy. Give us the hard bit. I was like, we're done. That was the whole content. And they were like, no, but physics is hard. We can't do physics. We can do this, but we can't do physics. They had this mindset, physics is hard, physics is for boys, we can't do physics, which might sound familiar to those of you who've ever tried to teach tech. It's exactly the same problem. This is a soapbox of mine. But it's something that comes up again and again every time I know people who've gone through year 12, they build their entire self-worth on this number and whether they can get into the degrees that they want to do and all of the things. But the ATAR does not measure whether you went the extra mile on a project that was meaningful. It does not measure whether you raised money for Oxfam during a humanitarian crisis. It does not measure your ability to build community. It doesn't measure any of the things that I think are really important. It also does not measure the things that we say are important. Every university that I can find has a statement somewhere on its webpage that says, we value critical thinking, ethics, problem solving. None of those things are measured at all by the ATAR. The ATAR is largely measured by time-limited recall and template-based problem solving. None of that is the stuff that we're going to need in real life. When you go to the doctor, do you ask what their ATAR was? Or do you want to know whether they can communicate and whether they can, how good a diagnostician they are and how well they know the particular area of speciality you're talking to them about? I don't care what their ATAR is. So we're back to scratch. And one of the problems with teaching tech in schools is that Scratch is beyond, even Scratch is beyond the reach of a lot of teachers because they've never done tech before. They haven't had the time to train in it. They haven't had the resources to train in it. They haven't been supported. We threw the digital technologies curriculum out as one big thing all at the same time, even though the year 7 digital technologies curriculum assumes that you've done prep to grade 6 digital technologies, and they haven't. They still haven't because teachers don't understand it. So what you get is you get kids who are taught by teachers who give them the equivalent of Tia's Photoshop experience. Do this, do that. So even in Scratch where they could be playing, they literally drag this block on, click this block onto it, do this thing. It's not very engaging. So the first time I did data science with the year 10s, when I persuaded my boss to put a little data science unit in, we did election data because I happened to have a student who was obsessed with politics. And I went and had a look, and on the AEC website, you can download the vote data. And sometimes it takes a bit of finding, but you can literally get the raw data. So I had a CSV file that had 3 million or so lines, which was every vote for the Senate in the federal election in Victoria. This was the ballot paper that year. You will notice it is not one-dimensional. And the CSV file had every vote was a string. And in the string, there was some stuff about the booth and the electorate and some other stuff that I never figured out what it meant. And then there was this flat string, which was for all of the boxes, there were 151 boxes, and the flat string was 151 long. Now, how do you map the flat string onto the paper? Because you can't just go left to right because some of the columns are longer, and I could not find anyone at the AEC who could tell me. Now, I do believe there must be people at the AEC who know, but I couldn't find anyone who could tell me that. So I had to figure it out myself. Basically through a lot of coding and hacking and knowing that, you know, Liberals and the Labour got more of the votes, and, you know, we got there in the end. And the kids had to come up with their own question. What can this data tell me? And of course, the first question they come up with is, well, who's the best party? I'm like, I wish that was represented in that data, but I don't believe that it is. What do you mean by best? You know, so then you have the whole rich conversation about qualitative versus quantitative and what can data tell you and what can it not tell you. The thing is, it took me so long to build this project. The only reason I could do it was because I was half-time and I had the skills already. Most teachers don't have the skills already and don't have the time to do this kind of stuff. So this is why I started ADSI, to try to shortcut some of that hard work so that I can give them the data sets. I can explain to them what they mean. I can give them the projects to run with the data sets. and kind of make it much easier for this kind of stuff to happen. So we've done projects on microbats, not microbits, microbats. You might not see it from the photo, but they are super cute and super interesting. And the data is messy as all get out because it was collected by volunteers and stuffed into spreadsheets where they had multiple tables in the one sheet, and it was really ugly to deal with. So again, they had to code. It wasn't complicated code. You know, most of them were writing Python programs that were like 10 lines long. But the thing is, they came out going, I wrote code. I did a thing, like, and it was meaningful. And I did it. And they kept coming back to me going, I didn't know I could do that. So the idea of doing something real and meaningful and giving them that feeling of, did a thing that I didn't know I could do. I don't care whether they come out with amazing Python skills. I care that they come out with the belief that they can. Everything else follows from that. So that's why I started ADSI. There's various information at the website, but we did projects. We've done projects on trees and carbon. That's a collaboration with Pawsey Supercomputing Centre in Perth. I really like that one. Projects on science journalism, evaluating the quality of science journalism. So you're going to come up with metrics and then figure out how your metrics are flawed and all that juicy stuff. We've done projects on litter. Litter's a really good one for the littlies because you can scale it up really easily. So your 5-year-olds are collecting the litter and then they're sorting it in piles. And it doesn't matter how they decide to sort it. It's just that they come up with their own sorting mechanism, and then they come up with, well, how do we make sure that there's less litter in our playground? And it's great too, because if they've done a litter survey one day, and then they implement some program to try and fix it, and then they do another litter survey, what's different between the 2 days when they did the litter survey? With the grade 5s out on camp one of the weeks, was it a windy day, so half the litter blew away? Like, they meet that idea that just because you measured something twice doesn't mean they're directly comparable, which is, you know, again, as soon as you get away from textbook stuff and do real stuff, you get all this richness and complexity for free. There's a whole bunch more projects. You can go rummage on the website if you want, but this is one of the bits of feedback that I really liked. The kids were suddenly using it everywhere. They could use it in everyday life, but much more exciting than I thought it would be. You know, they came into it going, this is gonna suck. And they came out with useful skills. And that's it. Like, that is the battle, right? Motivation is the battle. The rest of it doesn't matter if you haven't got motivation. And it's that idea that as soon as you're doing real projects, you're giving the kids power. You're giving them the power to create change. And the projects that really create change, that is my mantra. Data science is not tech skills. Data science is actually more about skepticism and critical thinking than it is about tech skills. You come down to these questions, these fundamentals. What is wrong with this data set? What is wrong with this analysis? What is wrong with this visualization? And what is wrong with these conclusions? What else could it mean? I'm assuming that my results mean that my project is the best thing ever. What else could it mean? How are the measurements flawed? Because no such thing as a perfect data set, no such thing as a perfect analysis, no such thing as a perfect visualization. You know, the idea that by default, you critically evaluate your own work, I think is incredibly powerful, and one I would like to see implemented in government. This is my favorite project template. It's where they find a problem the kids care about, they measure it, they analyze that, they communicate that, they propose a solution, they implement the solution, and then the bottom bit, like, we don't do that in government, we don't do it in education, we don't do it in business. We just implement the latest, greatest Kool-Aid and then move on to the next thing. Stop and measure it to see not whether it worked, to see how well it worked, who was helped, who was harmed, what can we do differently, how could it be better? Build that in from the start, that every project you do, you critically evaluate it and you assume it's not perfect. You cannot get 100% for your result. Can get 100% for your analysis of the problems. All right. So if you're interested in all of these ideas, there is the book. The book is available as a free podcast if you like your things audio. Raising Heretics, the podcast. It's also an ebook and a paperback. There are sample projects on here. And the podcast that Lewis mentioned before, which is a lot of fun. You should come on, by the way. If you know people I should interview, let me know. And I forgot to update that. I'm not on Twitter anymore, but I am on Blue Sky and Mastodon and all of the things, so you can find me easily enough, but the email address and the website work.
Any questions if people have them, and I put a message in the chat, so if anybody online wants to ask questions, I'm monitoring that.
So not really a question, I'm just going to say it's a pleasure when you talk about this stuff. Almost everything you said I really like, and I think, you know, it goes to some of my skepticism about some of the STEM activities that have gone on over the years. Partly a reason just from seeing my own kids go through it. It feels a lot like the STEM activities start by saying you're smart, you should do STEM, and then they patronize people and assume that all their decisions up to now, up to you received our wisdom, were either uninformed or irrational. And actually, when I know my kids smart, the reason my daughter chose not to do STEM were a lot to do with the artificiality of the activities that were sort of presented. And Photoshop, I think, was literally one of them.
Yeah.
She didn't have Scratch, she had some other programs. I've always been a bit skeptical about the Scratch as well. So I thought it was very interesting. I think the thing I wanted to say is that this doesn't just apply in high schools, this is really relevant in universities. And ATAR is not where that whole stuff stops. Like we do the same thing here.
Yeah.
Time limited tasks, recall becomes a thing.
Yeah. And
you have to regurgitate the known truth, because that's what mathematicians have done forever, is just regurgitate known truth. It's like completely the opposite of what we would like our students to actually be able to do.
And as universities, it's not what we say we put our students out with.
That's right.
We pride ourselves on all these attributes that we are not teaching or assessing in our students.
We constantly say, you know, critical thinking is the core thing for the teachers, and then ask them to regurgitate things. So I really like it. Thank you very much.
Thank you.
Well, I'll play. Oh, there's somebody else on my queue, but the URLs in the chat. Probably the best approach to make the reporting available or to follow up.
Yeah.
Maybe I'll be slightly skeptical, like devil's advocate, and ask how you assess this stuff. Because, you know, the thing about facts is that there is no set, right?
Yeah.
So,
No, I totally get that. So you have to assess the process, not the results. So that you're not measuring whether they can fake their prac results well enough to get past the, you know, the sniff test, but you're actually measuring their ability to say, here is where I went wrong. Here is stuff I could do better next time. Here is, you know, where it worked and where it didn't work, and the problems with the process, and that sort of whole thinking around it. Yes, more difficult. Yes, more time consuming. Yes, much more important. And I think, you know, we really have to throw away exams, which is, you know, going to send some people under the table crying and other people just twitching in the corner. But we really do. They are not useful assessment instruments. We have known that for a really long time. Let's move on.
I have to say one more thing, going back the other way. I don't think I've ever asked a student about their targets.
Yeah.
We take them in for scholarships, we like really supervise and do a whole lot of things. And I don't remember ever looking at that number. it's this one critical thing in their lives, and because of that takes on this super importance. It's really not.
We push so hard though that year 12 is the most important year of your life, which is rubbish. And you know that what you get into shapes your, it's, you know, and you have to get in. If you don't get in, it's all over. It's like there are so many pathways. There are, if you really, I didn't get into honors in computer science, but I wrangled my way in and wound up doing a PhD. Most of the people who got H1As and, you know, first class honors and you know, did amazingly well in undergrad, most of them never actually finished their PhDs, the people I was working with. So it's not a useful measure. Those numbers that come out of exams and ATARs and things, they're not useful.
All right, we better wrap it up because it's just gone past 11 o'clock. But thank you very much for talking with me. Thank you. That was trying to figure out how to stop this.